talk about Bohr's theory of the atom and use Bohr's theory of the atom to explain the individual lines that we see on a line emission spectrum of hydrogen. Right, before we delve into Bohr's theory of the atom and explain it and be able to draw it, there's 5 different definitions that we need to address first. Because at the end of this, you have to be able to write 4 bullet points explaining Bohr's atomic theory or relating Bohr's theory to the line emission spectrum of hydrogen. And there's certain keywords and key details that you need to include in your answer, and that's where the definitions come in. They're a great source of keywords that we can use in our answer. So up first is the definition for an energy level. Now, honestly, an energy level the definition is quite common in the exam, and it tends to come up for between 3 and 6 marks. It depends on the year how many marks are on offer for it. But what your examiner is looking for, an energy level is the fixed amount of energy an electron can have in an atom. That's it. Now, I'm going to break that down in a second and explain what it means a little bit simpler than that. But that's the bits in bold, that's what the examiner is looking for. Now, an energy level, they are given the symbol N. So when we draw our Bohr diagrams, we draw these rings around the nucleus. We are now going to call them energy levels. At junior cycle, you may have called them shells or orbits, but now we're moving on a little bit in the advancement of chemistry, so we want to start using more correct language. So we're going to call them energy levels. Right, so up first, you have your first ring around the nucleus. What I'm first going to label is the nucleus itself with that positive charge. Now, Bohr theory, we will only be talking about Bohr theory in relation to a hydrogen atom. A hydrogen atom has 1 proton and 1 electron, so we don't need to worry about loads of electrons on our diagram. That's why I've only shown 1 proton in the nucleus as well. Now, my electrons are sitting on these rings around the nucleus, like you would have drawn atoms at junior cert. So let's fill them in. If I was labeling my energy levels, the first ring around the nucleus, your first orbit, that's N is equal to 1. That's your first energy level. The lowest number energy level you can have is N is equal to 1. There's no such thing as N is equal to 0 or 0.5. The N values for energy levels are whole numbers. Now, that's N is equal to 1. When you move out from the nucleus and out from N is equal to 1, you are going up in energy. You're moving further away from the nucleus. So our next one is N is equal to 2, the second energy level. Then you move out again and we have N is equal to 3 and N is equal to 4. So from that diagram that I've shown, there's 4 energy levels on that atom of hydrogen. Now, technically, atoms have more than 4 energy levels, but to keep my diagram quite simple, I'm only showing 4 of them. Next, because I'm dealing with hydrogen, hydrogen only has 1 electron. So I'm going to draw in the 1 electron there. Now, when you are drawing electrons on a Bohr diagram, they have to be on one of the rings or one of the orbits around the nucleus. They can't be between energy levels. So I can't draw my electron there like that, between N is equal to 1 and N is equal to 2, because that's actually incorrect. Now, when my electron is in N is equal to 1, it's in an energy level, therefore it has to have a fixed amount of energy. Now that phrase, fixed amount of energy or definite amount of energy, that's a key phrase that you're going to see quite a lot in relation to Bohr's theory of the atom, and particularly in an exam answer. So that's a key phrase we're going to learn off. Now I'm going to fill in numbers here for the energy that an electron has in each of these energy levels. Now, honestly, I'm going to make these numbers up. I'm going to pick nice numbers that are going to give me nice numbers to subtract, and I won't need a calculator to subtract them, fingers crossed. So the first one, N is equal to 1. When my electron is in N is equal to 1, I'm going to say that the electron has 5 joules of energy. please don't write that on a test. 5 joules is way too big. It's actually nonsense. But it's a nice number that's going to subtract easily in a minute. But when my electron is anywhere on that ring or anywhere in that energy level, it has that specific fixed or quantized amount of energy. A quantized amount of energy just means that a definite amount of energy. It has a very fixed amount. In this case, we're calling it 5 joules. The next one, if we move up to n is equal to 2, I'm going to say that when my electron is in n is equal to 2, it has 10 joules of energy. Now, when my electron is anywhere in n is equal to 2, so if I rub it out from that one, and now I move my electron up to n is equal to 2. When my electron is anywhere there in n is equal to 2, it has 10 joules of energy, and it's moving. The next one, for n is equal to 3, I'm going to say my electron has 14 joules of energy. And then for n is equal to 4, I'm going to say 17 joules of energy. Now, where did these numbers come from? I made them up. So don't be panicking going, oh my God, where did these numbers come from? I literally made them up. Now, from here, before we move on, those numbers just represent a fixed amount of energy an electron can have when it's in a specific part of the atom. That's all it is. Now we're going to use this idea again in a minute to look at the ground state and the excited state of an atom. So next up is the ground state. It's the state where an electron occupies an orbital in the lowest available energy level, i.e. for hydrogen, it's n is equal to 1. Now if I fill out my diagram like I did in the other one, you have n is equal to 1 as the first energy level, n is equal to 2 is the second, n is equal to 3, and n is equal to 4. That first ring around the nucleus we said was 5 joules, 10 joules, 14, and 17. Okay. Now, in a hydrogen atom, there is only one electron. And when your hydrogen atom is in the ground state, your electron has to occupy the lowest energy level. And in this case, the lowest energy level is n is equal to 1. There's no energy level below n is equal to 1. So my electron is somewhere on that one. Now, it could be anywhere. It doesn't have to be exactly where I've drawn it on n is equal to 1. It could be anywhere as long as it's on that first ring around the nucleus. If my electron, say for example, I didn't draw it there. If I had drawn my electron here, in n is equal to 2, well, this atom is no longer in the ground state because my electron occupies an energy level above the one that's available for the ground state. Therefore, your electron is occupying an excited state energy level, or you can say the atom is in the excited state, which we're going to see on this one. Okay, so it's the state where an electron occupies an orbital in a higher energy level than those in the ground state. So your n value for the energy level is bigger than 1. If your electron occupies n is equal to 1 for hydrogen, that's in the ground state. And if it's n is equal to 2, 3, 4, 5, 6, whatever, as long as it's bigger than n is equal to 1, then your atom is in the excited state. So if I, if I drew this diagram, and I filled in my electron here. Your electron in this hydrogen atom occupies n is equal to 3. That is bigger than the energy level available in the ground state. Therefore, that atom of hydrogen is in the excited state, or the electron occupies an excited state energy level. If I was to draw this one, where the electron occupies n is equal to 1, that atom of hydrogen is in the ground state because the hydrogen's one electron occupies the lowest available energy level. Now, there's a reason I'm labouring over those two diagrams because in the short questions a couple of years ago, students were given a Bohr diagram for hydrogen and it showed an electron falling to n is equal to 2. And any student who used the phrase ground state in their answer actually lost a huge amount of marks. So be very careful and get into the habit of looking at what energy level is involved and where that electron is before you say ground state or excited state. Right, my last two definitions before we dig into Bohr theory is the atomic number of an element and the mass number of an element. So on the left-hand side of the screen, I've given you a little picture of carbon. Now, in chemistry, we're going to be using the formula and tables book a lot to figure out what the atomic number and mass number is. You're not expected to learn them off. You use your formula and tables book. That is on page 79. So I've just taken a little screenshot of just the carbon. Now, there's two numbers that carbon has on page 79 of your formula and tables book. The first one is the number 6. That represents the atomic number of an element. Now, the atomic number specifically represents the number of protons in the nucleus. Now, the atomic number of an element identifies the element. Every single element in the periodic table, whether it's carbon, beryllium, magnesium, manganese, cobalt, whatever, every single element has its own unique number of protons. The protons in the nucleus actually determines what the element is. So if you have an unknown atom, but you can figure out that there are 6 protons in the nucleus, well, straight away, based on the protons, you know that that atom has to be a carbon atom. It can't be anything else. Only carbon will have 6 protons in the nucleus. The number of neutrons will be different depending on the isotope, and we'll see that in isotopes a little bit later. Next up is the mass number. Now, the mass number that you see on page 79 of your formula and tables book, most of them actually have a certain number of decimal places. That's something that we're going to address a little bit later in the relative atomic mass calculation when we see it in relation to isotopes. So we're just going to go with it for now and say that carbon has a mass number of 12. I'm going to ignore the 0.01. The mass number is the number of protons and neutrons. So it's 2 subatomic particles added together. Now, when you're looking at the periodic table, there's always 2 numbers that you see, the atomic number and the mass number. Based on how it's printed for the Leaving Cert, the atomic number is on the top and the mass number is on the bottom. But it's a better way to look at this if you think of it as the smaller number is always the atomic number and the bigger number is always the mass number. Because when we start looking at nuclear formula, those numbers are the other way around with the mass number on the top. Whereas if you get in the habit of looking at it in terms of the bigger and the smaller number, you're not going to get caught out in relation to that. Now underneath, each element has a unique number of protons in the nucleus. The number of protons in the nucleus of an atom identifies the element. At the bottom of the page, 3 elements are shown. Carbon has an atomic number of 6, nitrogen has an atomic number of 7, and oxygen has an atomic number of 8. So every element has its own unique number of protons in the nucleus. Now, if I wanted to count the subatomic particles, let's take carbon, for example. Now, the atomic number we said is the number of protons in the nucleus. Well, carbon has an atomic number of 6, therefore it has 6 protons in the nucleus. In a neutral atom of carbon, the number of protons is equal to the number of electrons. Therefore, my carbon has to also have 6 electrons. To work out the number of neutrons, that's what the bigger number is going to be used for. That 12 that we see on carbon is protons plus neutrons. We already know the number of protons is 6, so to find the neutrons, it's the mass number, which is 12, minus the atomic number, which is 6. So carbon has 6 protons, 6 electrons, and 6 neutrons. If I was to look at oxygen over on the right-hand side, oxygen has 8 protons because the atomic number is 8. Protons is equal to the number of electrons, so we've got 8 electrons. And to work out the number of neutrons, it's 16 minus the atomic number, which is 8, so we have 8 neutrons. Now, just because I happen to pick 3 elements, when you subtract the mass number and the atomic number, the number of neutrons is working out the same as the protons and electrons. That's not always the case. There's quite a few elements and isotopes where when you subtract the mass and the atomic number, you will have a different number of neutrons than the protons, and that's fine. Right, next up, let's start in with Bohr's theory. Now, this technically leads off of history of the atom. Now, in history of the atom, we started looking at different scientists and their discovery of the subatomic particles. One of the most important scientists that you learned about was Thomson. Now, Thomson came up with the plum pudding model of the atom, where you have a sphere of positively charged matter and you have electrons randomly embedded in the sphere. Now, I always like to think of that as a blueberry or chocolate chip muffin, where the muffin batter is the positive sphere, and then you've got your chocolate chips randomly dotted throughout it. That's what the plum pudding model technically looked like. Nobody eats plum pudding anymore. It's disgusting. But Bohr took over after Thomson had been studying the atom. Technically, it was after Rutherford. Now remember, Rutherford developed the theory of the atom again because he discovered the nucleus. He discovered that most of the mass of the atom is centered in the middle of the atom, and then you have your electrons around the nucleus. Now, Bohr ran with that idea and he came up with his atomic theory to describe the layout of an atom, where you've got the nucleus in the middle and then you've got your electrons going around the nucleus in fixed paths called orbits. So on the right hand side, I'm going to show you what a diagram of Bohr's atom of oxygen would look like. Now, thankfully, the junior cycle wasn't a complete waste of time. When you were drawing atoms at junior cycle level, they were actually Bohr diagrams and they are useful here. So that's not going in the bin. We're going to keep that. In the center, you have 8 protons in the nucleus for oxygen, and you have 8 neutrons. That's my nucleus of an oxygen atom. Then you have your first energy level around the nucleus. That's supposed to be a perfect circle. We're just going to go with it. And we're going to label that as n is equal to 1, the first energy level. Now, oxygen has, we said, 8 protons, 8 electrons, and 8 neutrons. Well, your protons and neutrons are already filled in. Now we need to fill in the electrons around the nucleus. You have 2 electrons in the first energy level, and there can't be more than 2 in the first energy level. The first energy level is full, move out. Now we move into n is equal to 2. In the second energy level, that can hold a maximum of 8 electrons. We have 8 in total in oxygen. You've already got 2, so that means n is equal to 2 will hold 6 for oxygen. It can hold up to 8, but then there would be too many electrons for oxygen, so it's 6. Now, that's what the Bohr structure of an atom looks like. And we're now going to use that idea to explain the line emission spectrum of hydrogen, but we're going to dig into this a little bit more first. Now, the line emission spectrum of hydrogen looks like that picture there. It has a black background with coloured lines on it. And each of those coloured lines represents an electron falling from a higher energy level to a lower one. So from that graph, you can see that there are 4 coloured lines. That means there's 4 coloured lines produced when an electron falls from a higher level to a lower one. There's 4 electron transitions in the visible region. Now, if that sounds like a little bit like I'm speaking a foreign language, it's grand. It should be a little bit difficult. By the time we get to the final step, when we look at the Paschen, the Balmer, and the Lyman series of lines, what I just said will make sense. Right, so the worked example. Now, to be honest, in the notes, I've put a whole A4 page going in, explaining and fleshing out what happens in Bohr's atomic theory. And I drew you a lovely diagram showing your electron moving up and down energy levels and what happens there. To be honest, we're going to go into what you need for your exam, and we're going to try and condense that a little bit. Now, what I'm putting here is the shorter version of what's written out in full in your notes. And this worked example is also written in your notes, and I'm going to recreate it here to show you what your examiner is looking for. It says, use Bohr's atomic theory to explain the line emission spectrum of hydrogen. So that's asking you to explain why we see these coloured lines on the black background for hydrogen. Right. To help me with this, I actually recommend that you draw the Bohr structure of hydrogen. Now, Bohr diagrams, or Bohr's atomic theory only works for hydrogen. So while we use it to represent other atoms as well, it really does only work for hydrogen. So, hydrogen has, you have your proton in the nucleus, then you have your first energy level, which is n is equal to 1, and that's where I'm going to put the electron. Now I've drawn 4 energy levels for hydrogen. So we've got n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. Now, just using that diagram for hydrogen, we're going to use that to build the first bullet point explaining this theory. So there's 3 pieces of information I need to give here. When I drew that diagram of a hydrogen atom, I specifically drew the electron on one of the rings. That means your electron has to occupy an energy level. It is restricted to an energy level. So there we go. There's my first point. Your electron is restricted to energy levels. Now, not only that, when I was doing this out a few minutes ago, I had specific energy values on those energy levels, which I'm going to label now. When your electron is in n is equal to 1, I said that was 5 joules of energy. N is equal to 2 is 10 joules. N is equal to 3 was 14. And n is equal to 4 was 17. So that means your electron has a specific or fixed amount of energy. Now, that phrase, fixed amount of energy, is something that we're going to try and shoehorn in here because it's the very key essence of what a Bohr theory question is asking you for. So, your electron has a fixed amount of energy, or a fixed energy value is fine. Now, that's not enough. We want a little bit more. Which specific energy level did I put that electron in? I put it in the lowest available energy level. Therefore, that atom is in the ground state, or the electron occupies a ground state energy level. So I'm going to say the electron occupies the lowest available energy level. Now, when I go through this with my 6th years again in 6th year, so I covered it with them in 5th year, but I do it again in 6th year when it makes more sense to them. They do that first bullet point and go, oh my God, that's overkill. Do I really have to include all of that? Yes. The worked example answer that I have written in your notes is written based on the previous mark schemes for this question. So if it's in those bullet points, it has to be in your answer, specifically the words in bold. There has been multiple mark schemes where a combination of those 3 points for that first bullet point are needed to get the first 3 marks. So we're going to cover ourselves and make sure that we have all 3 of those small points in there. Yes, it is overkill, but we're just going to go with it. Now, how do I know how many marks are on offer here? Because the question has 12 at the end, that is a 12-mark question, which means the examiner is looking for 4 separate bullet points. There's your first one, so that's your first 3 marks. Next, you can make your electron move up in the energy level. So at the minute, it's sitting at n is equal to 1, but we want it to move up to a higher energy level. Now, to do that, when your electron is in n is equal to 1, it has 5 joules of energy. If I want it to move up to n is equal to 4, for example, Your electron is not going to spontaneously move from having 5 joules of energy up to 17. It can't just magically, mystically gain a certain amount of energy. That energy has to be provided to the atom in a specific way. So that's where you come in. Your atom absorbs a very specific amount of energy. So your atom absorbs a fixed amount of energy. According to my diagram, to move from n is equal to 1 to n is equal to 4, my atom would have to absorb 12 joules of energy. How do I know? Well, to get from 5 up to 17, you have to absorb 12. It's because it needs to get those 12 joules of energy from somewhere. Now, where does it come from? It comes from heating or an electric current, which I'm going to write in. It's important that you recognize how that energy could be provided. So heating or electric current. Next, when that happens, now once your atom has absorbed that amount of energy, an electron can move up to a higher energy level. The electron can jump. Now here, resist the temptation and the urge to start abbreviating. No, while this is not an English exam, keywords are important in chemistry. You can't just start abbreviating throughout your answer. So spell out the word electron and spell out the word higher energy level. Don't just go excited state or ES. Don't do that. Now, so your electron can jump to a higher energy level. 3 marks. So if I was to change that diagram so that now I'm moving my electron from there, and I'm going to move my electron up to n is equal to 4. Oh, no. Meant to be in blue pen. There we go. So my electron is in n is equal to 4, where it has 17 joules of energy. That atom is unstable. Your electron could occupy a lower available energy level. Now, the word unstable is vital here. If that one word is missing in this answer, you are highly likely to drop 3 marks, even though it's only one word. So your atom is unstable. Now, how is it going to get more stable? Well, it moves down in energy. Your atom is going to lose energy when the electron falls. So your electron drops from n is equal to 4 to any of the other lower energy levels. Now, I'm going to pick a specific one. I'm going to say my electron is falling from n is equal to 4 to n is equal to 2. So my electron is dropping from where it had 17 joules of energy to where it now has 10 joules of energy. So you could be asked, what would you see happening here? Your atom is unstable, so your electron falls from a higher energy level to a lower one, to a lower energy level. Be careful of your language. Now, don't say ground state here. Get out of that habit. The electron for hydrogen does not have to fall back to the ground state. And according to what I have shown in that diagram, it actually hasn't gone to the ground state because your electron is in n is equal to 2. That's not the ground state energy level. So be careful. It's still technically an excited state. A more correct way to reference this, and something that will get you marks every time, is you just need to say higher energy level to a lower one. That's it. You don't need to say from the excited state to the ground state, because technically that would not be applicable here, according to what I have shown in the diagram. Now, you're losing energy, or energy is going to be emitted from the atom because you're going from 17 joules down to 10. You can't just make 7 joules of energy disappear. It's actually given off in the form of light. And a photon of light is emitted. Brilliant. Now, so here, a photon of light with a squiggly arrow is kicked out, and the amount of energy that that photon has is the difference in energy between the two energy levels. So that would be 17 minus 10 according to my diagram, which would be 7 joules. Now, what I just did there is actually the fourth bullet point that the examiner is looking for. They're looking for how do you calculate the energy of the photon that's emitted from the atom. It's the difference in energy between the higher energy level and the lower one. That's why I picked nice handy numbers to subtract. Now I'm going to write a formula for this. We have E2 minus E1 is equal to HF. You do not just leave it like that, because E2, E1, H and F, we haven't told the examiner what that is. You can't just plonk the formula down and expect the examiner to know what you're talking about. Now here, we need to tell them what the symbols mean. So I'm going to backtrack through my answer and fill in what E2 and E1 is. E2 is the energy of the higher energy level. So I'm going to put that in here. Can jump to a higher energy level with fixed energy value, which is E2. It's unstable. The electron falls from a higher energy level to a lower one, which we'll call E1. That's the energy value of the lower energy level. Then H we'll call Planck's constant. And F is the frequency. Right, so there's the first formula that you have seen in chemistry. Now, don't have a heart attack. You will never at Leaving Cert Chemistry Lab have to put numbers into that formula. However, it's useful to learn off E2 minus E1 is equal to HF, because then it means I don't need to write out a sentence explaining that the energy of the photon is equal to the energy of the energy of the higher energy level minus the energy of the lower energy level. It's a shorter way to say the same thing. So it means we're not spending ages writing 4 bullet points. Now, that is your perfect Bohr answer for 12 marks. If something like this for 12 marks is taking you an A4 page and a half because you're so enthusiastic, you've learned off loads of great stuff about Bohr, and you're trying to show the examiner all of that good stuff, it still doesn't matter. You're still only getting 4 bullet points out of it for 12 marks. So we need to try and cut your answer down a little bit, and you need to start timing yourself. An answer like that, it took me longer because I'm talking, of course I am, but if I was writing that out, you need to be trying to restrict yourself to 4 minutes. At this stage, if it's the first time you've seen Bohr's atomic theory, I don't expect you to be able to write off all 4 bullet points at this particular stage and get full marks each time. How you're going to nail this question is you need to sit down with a blank piece of paper and write it out. Honestly, it's going to take about 10 attempts before you're going to get this absolutely perfect, and it is worth it. Bohr theory did come up in 2024, however, it didn't come up in its fullest glory. So just to be on the safe side, make sure you cover it for your exam. Now, next up, we're going to have a look at some useful keywords. So the first one is the word spectroscopy. Spectroscopy is the study of absorption and emission of light by matter. It looks at how matter interacts with light, how much light is absorbed, what the energy of light is, and how much energy of light, or what the energy of the light emitted is. The word spectrometer. Now, this caught everyone in 2024. This is the machine that carries out the analysis. So you've got a big box, you put the sample into the box, and then the spectrometer, which is the box, does the analysis for you. It looks at how the sample interacts with light. So the spectrometer is the machine. Spectrum is plural, and spectrum is one, and spectra is plural, more than one. This is the image that the spectrometer produces after the analysis. It's the graph that it gives you, or the series of data that it gives you. So if it gives you one image, that's a spectrum. If you do more than one analysis, that would be a spectra for more than one. Now, next, before we look at the line emission spectrum of hydrogen, there's something that's missing from the junior cert that actually would be helpful here. Of course it would. And it's the idea that light is made up of different amounts of energy. So over on the right-hand side, you can see the 7 different regions of what we call the electromagnetic spectrum. We have radio waves, microwaves, infrared, visible light, which is the light that we see, ultraviolet, X-rays, and gamma rays. The only type of light that our eyes can see is visible. We can't see any of the other 6 types of light, but that doesn't mean it's not there. So when you look at a rainbow, if it's raining and sunny at the same time, light hits the water droplet and it splits out into different colours because white light is made up of 7 different colours. You have red, orange, yellow, green, blue, indigo, and violet. That's the Roy G. Biv acronym or mnemonic. Now next, all I really want from that is to introduce this idea that light is made up of colours of different energy. And now that's going to lead us into the line emission spectrum of hydrogen. Right. Now, this next section is something that students really struggle with, and it's something that is going to take you a little bit of sitting down and figuring it out. It is going to be quite difficult the first time you see it. However, there's very little here that you have to be able to do. Number 1, you have to be able to explain why each element has a unique line emission spectrum. And number 2, you need to be able to name the 3 series of lines in the hydrogen emission spectrum, the energy level the electron falls back to, and the region of the spectrum. So UV, infrared, and visible. They're the 3. Now, we'll get into that in a minute. So let's start off. Let's learn to walk before we can run with that. Right, the definite amount of energy emitted when an electron falls from a higher energy level to a lower one appears as a line of a particular colour if the electron falls back to n is equal to 2. If it doesn't fall back to n is equal to 2, it does still produce a photon of light. It's just not visible to the naked eye, so it's not colour. Each element produces a unique line emission spectrum. It actually acts as a fingerprint because every single element in the periodic table has a unique electron configuration, which gives rise to unique electron transitions. So unique electron transitions, different electron or unique electron configuration. That's actually a 6-mark answer. On the right-hand side of the screen, you can see the line emission spectrum of helium, hydrogen, and neon. As you can see, the lines appear in different regions. That's because they all have a different number of electrons, and your electrons are moving in different ways inside each of those atoms. Now, this next bit, this is where I find students really struggle with this. They don't understand what the Paschen, Balmer, and Lyman series are. So I'm actually going to show you the full line emission spectrum of hydrogen and split them into the bands for you. There's 3 series of lines in the line emission spectrum of hydrogen. It's specific to hydrogen. And the names of them are Paschen, P-A-S-C-H-E-N, Balmer, and Lyman. These emission lines appear in different regions of the electromagnetic spectrum. Technically, our eyes can only see one of them, the Balmer series, because they're in the visible region. Now, don't panic. You don't need to be able to do anything with this diagram, and you will never be shown this diagram in the exam. But if you look down at the bottom where the lines are, we're looking at the red ones, you can see that there are 3 approximate bands or 3 individual sections on that diagram, and I'm actually going to highlight them. So the first series of lines are the Lyman series. These are over here. Now, they are not visible to the naked eye. The next series of lines are these ones here. So the next band that we can see is here. They are called, collectively, the lines that you see are called the Balmer series of lines. They're actually named after the scientists that studied these individual spectra. And then the third one, I'm going to pick a different color. Let's go with a nice pink. Is over here, the Paschen series of lines. It's actually quite a big one. Now, so they are the 3 series of lines. Now, you're not going to be given that diagram in the exam, and the examiner is not going to go, identify the Paschen-Balmer and Lyman series on that graph. But I find students, when we mention the Paschen-Balmer and Lyman series, they don't know how to connect them together. Basically, you get the line emission spectrum between the infrared and the UV, and this is what it will produce for hydrogen. Now, the only one that you can see is the Balmer series of lines. They're the coloured lines on the black background because we see coloured lines as coloured light. The infrared and the UV region, they'll still have lines, but they won't be coloured because they're not in the visible region. Now, on the next page, the series of lines in the hydrogen emission spectrum. So we have the Paschen-Balmer and Lyman series. Now, don't have a heart attack. Again, you're not going to have to label this diagram, and we're going to take it step by step, and I'm going to draw it with you. So the three series of lines are shown. Now, if you look on the left-hand side of that diagram, you can see n is equal to 1 for the first energy level, n is equal to 2, 3, 4, and 5. Now, what that is, because a lot of people get confused with this. Apologies, I didn't realize I was still on the highlighter. What that is this. You have your nucleus in the middle. You have n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. This diagram is only looking at a small section of one of these. So it's like you took a segment out of one of these diagrams, like that. That is what this is. Okay? It's just a lot easier to show it when it is flat like that rather than trying to show all of the whole diagram of the atom, because it's going to get messy very quickly. Right, the most important information from this. If you go over to the right hand side, see where it says P is equal to 3, B is equal to 2, and L is equal to 1. That's what you need. So P, B, L, 3, 2, 1. That's how I remember it. Now, I typed this into ChatGPT. I hate coming up with mnemonics. I am the worst person for it, and I can spend hours trying to come up with some way to remember the order of this. It's not going to happen. So ChatGPT helps me with this. Now, sometimes it spits back really awkward ones. It came up with, please inform 3, bold visitors 2, leave us 1. So they are the three series. And I'll go into them now in a second. We're actually going to deal with them one by one. But before I move on, I need you to highlight something on this diagram. So go down to the Balmer series. It's the left-hand side of the memory aid, and highlight n is equal to 3 to n is equal to 2, produces a red line. That's important. Right. Let's start off with the Balmer series. Now, in order for me to do this properly, I need a properly labeled diagram. So I have n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and n is equal to 5. Don't look at the other two series. I'm only looking at the Balmer series right now. So they're the ones in the middle. Now, in order for you to see these lines in the Balmer section or the Balmer series of lines in the visible region, your electron has to be falling back to n is equal to 2. It can't be falling to n is equal to 1 or 3. So if my electron was in n is equal to 5 and it fell from n is equal to 5 to n is equal to 2, the photon of light that is given off from that transition, n is equal to 5 to n is equal to 2, is this one here. You would produce a photon that is blue. So if you were looking at the line emission spectrum of hydrogen, that would be the blue line that you see on the hydrogen emission spectrum. Because if it is emitting blue light, well then it has to be the one that corresponds to blue light on the line emission spectrum. If your electron is falling from n is equal to 4 to n is equal to 2. Now, this will be a smaller transition because your energy levels are closer together. But still, n is equal to 4 to n is equal to 2, that will give us a cyan line. So that would be cyan. Cyan is actually one of my favorite colors. It's like a greeny blue. So the photon that will come off there is cyan. if your electron falls from n is equal to 3 to n is equal to 2, this will release a red photon. Now that one you need to remember. This is potentially worth 6 marks in your exam. N is equal to 3 to n is equal to 2. That's your first 3 marks. That's the transition. That's the electron falling. That's the higher level to the lower one. And the red photon is another 3 marks. For the rest of the colours that I've given you for the Balmer series, you actually don't need to learn off those colours and transitions. But you do need to know that the red one is n is equal to 3 to n is equal to 2. Now, the Balmer ones, they're the ones that we see within the visible region. They're the ones with the coloured lines on the black background. So if you look at that line emission spectrum in the middle of the page, that black background with the coloured lines, each one of those lines represents an electron falling from a higher energy level to a lower one. Every single one of them. Now, the red one is n is equal to 3 to n is equal to 2. Then the next one, you have n is equal to 4 to n is equal to 2. But the key thing that they all have in common is the energy level the electron is falling back will always be back to n is equal to 2. Now, that makes them the Balmer series. If your electron falls back to any other energy level, well then you're not going to produce one of these coloured lines in the Balmer series. You will produce one of the other two, which is the Lyman or the Paschen series. So if we move on to the Paschen series. Now remember, for your way of remembering this, we have PBL 3, 2, 1. We've talked about the Balmer series, now we're dealing with Paschen. This is where your electron is falling from a higher energy level to n is equal to 3. So your electron will always come back to n is equal to 3, which is here. So if it falls from n is equal to 4 to n is equal to 3, n is equal to 5 to n is equal to 3. Both of those transitions from my diagram will produce photons in the infrared region. Now, the infrared region can't be seen by the naked eye, but the photons still do have energy, so they will produce lines on an emission spectrum. They just won't be coloured. Now, that's all the Paschen series is. So Paschen, P for passion, not P-A-S-S-I-O-N. It's Paschen, P-A-S-C-H-E-N. Chemistry isn't a spelling, or it's not an English exam. We don't really care about your spelling, but spell it out as you sound it out, basically. Next. The last one that we need to deal with is the Lyman series. Now, this is if we've already dealt with n is equal to 3 and n is equal to 2. The last one is if your electron falls to n is equal to 1. That will produce a line in the Lyman series, which is in the UV, or the ultraviolet region of the spectrum. So all you need to know here is any of the higher ones down to n is equal to 1, so 3 to 1, 4 to 1, 5 to 1. All of these photons that are being emitted here, all of those photons will appear in the ultraviolet region. So what do you need? You need to be able to name it as Lyman, know that your electron is falling to n is equal to 1, and that's it. That's all you need to know from that, and it's in the UV. So if I go back to where I was a second ago, back to here. So what ChatGPT spat back for remembering the order is, please inform 3. That is Paschen, infrared, n is equal to 3. That's your first one. Bold, visitors, 2. Balmer, visible, n is equal to 2. Leave us 1. Lyman, ultraviolet, n is equal to 1. Now, if you want to come up with your own memory aid for remembering PBL321, then IVU, I don't really care. It's up to you. As long as you can name the 3 of them, give me the region of the spectrum, whether it's infrared, visible, or UV, and the energy level the electron is dropping back to. That's all you need. You're never going to be given one of those absolutely disgusting diagrams and asked to label it. That's not going to happen. So if you know the bare basics of that, that's all the examiner is going to be looking for. And on average, that tends to be between 3 and 6 marks if you can just name the scientists, give me the energy levels and the region of light. An absolute push. And also know that n is equal to 3 to n is equal to 2 is going to produce a red photon of light. Right, we're going to leave it there. That is a whole heck of a lot of information all in one go. What I would recommend doing at this point is sit down with a blank piece of paper now, draw yourself a Bohr diagram of hydrogen and see, can you come up with the 4 bullet points needed to explain the line emission spectrum of hydrogen? If you can get 2 of the 4, I'll be happy with that at the minute. Then go off, have a look at the exam questions and start trying some exam questions on Bohr theory. The more you get used to using the language that comes up here, you're going to have a much easier time when it comes to looking at atomic theory in terms of sublevels and orbitals and all of that good stuff, which is coming next. Right, hopefully that was beneficial and hopefully we learned something.